Alright, so this is the video for homework 3.1, Transverse Waves. So, let me zoom in. So these are just general waves, like snake on the concrete. We're going to determine the wavelength, which I do in blue, the frequency, dabbing, and the speed, or another word for speed is velocity, so letter V regular. For each wave, don't forget the units, and from the notes that we just took, we have one equation, so it's pretty easy to know what equation to use when you only have one equation so far. But the equation we've got is that the velocity is equal to wavelength multiplied by frequency. So I'm going to copy paste this over here so I have it on my paper. Velocity equals wavelength times frequency. This is the equation I'm going to be using for the whole assignment. So problem number one, actually, I'm going to do this one so that I can zoom in and still have my equation be present. So for part B, the wavelength, I need to decide what the length of the wave is from either crust to crust or trough to trough, but since it kind of starts here at the beginning of the up cycle, I'm just going to go, okay, from the beginning of the up cycle to the next beginning of the up cycle, so from there to there, this is my wave. The distance between there and there is 0.2 units are meters. If the frequency is 0.5, hertz is the same thing as 1 over seconds, but we'll leave it. Then the velocity is going to be wavelength times frequency equals velocity. Wavelength, get my calculator here. Wavelength times frequency, oops, too shiny. There you go. Wavelength times frequency equals velocity. This wave is moving at 0.1 meters per second. So going back to the first one that we skipped here, it gave me the velocity. It says that my velocity is 0.67 meters per second, but I need to figure out the frequency and the wavelength. And the wavelength I just get from the picture. From here to there, the wave is measuring at 4 meters. I'm solving for the frequency. So if V equals wavelength times frequency, V equals wavelength times frequency. I don't know what this is. I'm going to solve for it. 0.67, divide that 4 across. I should have done it like this. There we go. 0.1675 can either write per second or hertz, or here's a fancy way that I like to do it. Just because we do it in AP chemistry, so I tend to like to prep you guys for AP chemistry. 1 divided by seconds is the same thing as doing seconds to the -1 power. So I'm going to do 0.1675 seconds to the -1 power. Inverse seconds, if you will. All right, so there's the top part. Let me zoom out so you can get the full page to catch up. All right, now going off of that same thing, you're going to complete the table below. It's the same exact calculation. Velocity equals wavelength times frequency. Except for instead of having a picture to go off of, you are going to be using the graph. So here is the frequency, the wavelength, and the wave speed is fancy lingo for velocity. So this times this equals this. So pause the video and go through and fill in these blanks here. Frequency times wavelength equals wave speed. My wave speed is 300. Okay, pause the video and then at least do a couple on this chart. Did you finish it? Did you finish it? Did you finish it? Okay. Whoop, here's my answers. So then questions, we're going to analyze what happens to the frequency if the wavelength doubles and the speed does not change. So I need to find some examples in my chart here. So I'm looking for an example where the speed doesn't change, but the wavelength was doubled. So I'm thinking these two are a good comparison because look, the speed isn't changing. It's still 300. Oops, wow, that was really great of me. No, this is a bad example because the speed is changing. Sorry, let's look. Let's find one where the speed is not changing. Okay, sorry. I had like a laughing fit. Okay, so I meant to highlight these two here. So 500 and 500, and we'll just cross this little 300 out for right now. Oopsies. We'll use that later. So speed does not change, 500, 500. And we're wondering what happened to the frequency if the wavelength doubled. So it used to be 1 meter, but then it doubled from 1 to 2, doubled. The question is, going the same direction, what's happening here from 500 to 250? As this side doubles, this side is getting halved. The speed is staying the same. So what happens to the frequency if the wavelength is doubled? If the wavelength is doubled, then the frequency, what you'd write here is the frequency is getting halved. Okay, I'll let you do part B, but I'll help with the last one since I like had a brain fart for part A. What happens to the speed, okay, if the frequency decreases by half and the wavelength doubles? Okay, so let's find an example of that here. Or we could do part B. I'm only going to do one of them with you. What happens to the wavelength if the speed decreases by half and the frequency does not change. So actually I want to do this one because I can see where this example is already. The frequency does not change. That's going to be here and here. And we're wondering what's happening to the wavelength when the speed is decreasing by half. So from 80 to 40, that's halving. The question is, what's going on here? And this is also getting halved. So that's what you'd write. Basically, this section is just to show you the maths with a visual. Then we're taking away your visual and we're asking to do just the maths and analyze the relationships that they have. And now this last part, we're actually just focusing on the relationship, what relationship exists between the different variables. So number 4, make a scatter plot, graph of the information in the table, draw a line of best fit, assume that frequency is the independent variable. That means that we're going to put it on the x-axis. Be sure to include a title and axis labels. So frequency is going to be down here. Oop, I should have done this in red, but I didn't. Oh well. Frequency and wavelength. Let me get my units in here, inverse seconds and meters. And the wavelength, I need to go from about 2 to 6. So let's see. Let me see how I space this out. Okay, so what if I do 0.0 and I kind of, that'll be 1, 2, 3, 4, 5, 6. That'll work. And the frequency needs to go from 60 to like 180. So let's see. Okay, so what if we just do like that little break thingy in the graph, and we'll start here at, this can be 60, 70, 80, 90, 100. And that'll be great because then this will just be 170 on that line and we're barely above it. All right, so pause the video and actually, I'll do it with you. We got to graph the points. So at 171.5-ish, we're at 2. It's not the best graph I've ever done in my life, but it'll work. 107.2. Something like that. Draw a line of best fit. Okay. Well, it looks like that's my line of best fit, kind of a curvy thing there. When we've got that downward curve means that we have an inverse relationship. When the wavelength is going up, the frequency is going down. They run opposites of each other. So you get a curvy line like this. If you were to get, let me draw you some other examples. If you have a graph that does this and goes up linearly, when one side increases, the other increases, or they both go down. When they run in the same direction, then that's a direct relationship. When they run in opposites and make a curve, then that's an inverse relationship. So my title here is going to be, I don't know, relationship between wavelength and frequency. The answer is that it's inverse, because if I have a wave that's got really big lengths between the waves, like woof, 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 wow, that is such a big wave. The wavelength is really, really long. It's not happening very frequently. But if I have a wave that's like, whoops, and the wavelength, look at how close those waves are together. Super duper tiny, super duper short wavelength. The frequency is like, the frequency is high when the wavelength is low. When the wave is really, really chunky and big, it's not very frequent. So that's what it means by inverse relationship. So making sure you go back and you finish the ones that I skipped. I had just a few of them. This is homework 3.1, transverse waves.